it's a recurrent speaker in HPC KP. I'm very happy to welcome again Eduardo Arango, Senior System Software Engineer at NVIDIA. He's not going to give us one talk, but two. So, do you prefer to have one, then question, the second, then questions?
Yes.
Okay.
That way I get to drink water.
Okay. So I'm just telling the first one, and then I'm going to introduce him again and tell the second one. So the first one, it's not about just GPU anymore. Yes. Topology-aware declarative resource orchestration for the post-device plugin era.
All righty. You hear me? All good? OK. So, hey, it's nice to be here again. Last year I couldn't come, but it's always a pleasure to be here in Barcelona and share with, which I know is a very academic crowd of HPC, what we are doing in the open for cloud-native Kubernetes containers, and basically where I spend my life working on. And my message this year is not just about GPUs. Like, I want to take the knowledge of NVIDIA that we are not just GPUs anymore, and all the work that we are putting towards containers and Kubernetes is not just about GPUs. The first thing is, for all of you that have used or have at least tried HPC on a Kubernetes cluster, you know that the way you request a GPU on a Kubernetes cluster is, or used to be, this, which is very static and doesn't fully allow you to experience or enjoy the awesomeness of Grace Blackwell, upcoming Beta Rubin, or not even 8100 GPU, right? Like, when you request a GPU like this, you are wasting a lot of resources. So what are we doing as a community to make this better? I'm about to show you. So it used to be an integer. No topology, no partitioning. Basically, you were getting a GPU, and if your cluster is a heterogeneous GPU with A100s or H200s, or even like previous L40s or things like that, you will get a GPU. You don't know which type of GPU you are getting. But now, also, a problem that we are facing is the rack itself is a GPU, right? Like, the rack itself is a node. So during the first speaker dinner, we were talking about this, right? Like, now we can see the entire rack as one node. And this is a current problem for Kubernetes. When we installed Kubernetes for the first time on one of these systems, and we were checking the node status of Kubernetes, it was reporting that each node had like 400 CPUs and like infinite memory and infinite number of GPUs. And it was all because each kubelet on each node was reporting the memory and the CPU count of all the nodes in the rack. But each kubelet is deployed on each node. So it's crazy. So we are doing a lot of work in the community to teach Kubernetes that compute systems are changing. It's not just nodes connected with some sort of fast interconnects, InfiniBand, but now we have processes and hardware architecture that can make an entire rack to look as one node, two processes. And to get Kubernetes to understand this has been a lot of work, and there is still a lot of work to be done. There are some things that we are still working as a community. I will be showing the roadmap today. And for those that don't know, this is called the multi-node NVLink, or in software we call it IMEX. And this appeared from the Blackwell architecture, and also Rubin, Beta Rubin is going to build on top of this, where you can have 72 GPUs running as they are one in one node, which is pretty awesome. But counting devices and describing the fabric are two different things. So as of last year, everyone was running Kubernetes with device plugin. The device plugin, as I call it, device plugin era, was what we as a community thought was enough to inject special devices into pods running on a Kubernetes cluster. It was a static, just we thought just integer count only, we could just inject special devices into pods, but we didn't count as a software community that hardware was going to get more dynamic and more programmatic. and we need to do something. So what we did is we can do a rake scale reality now. By using DRA, that is a new way of injecting special devices into Kubernetes, we are now replacing the device plugin. And with the device plugin, we can even do topology and NUMA-aware scheduling on Kubernetes, which used to be a HPC-only feature. So now, and as I was telling some people during the breaks, now you can do this. You can do topology-aware scheduling, NUMA-aware scheduling in Kubernetes. You can do fabric-aware scheduling in Kubernetes. Like you can tell Kubernetes, run this MPI process, but only run it on systems that are connected by NVLink and that are close to each other. Like you can be that specific to Kubernetes today. But how? I will be telling you. So who I am and why I'm here talking about this. I work for NVIDIA. I've been working in multiple projects, and everything I do is in the open. And my interest is always to help people run HPC better every day, as fast as they can. I contribute to Kubernetes. I contribute to as many open source projects as time is possible for me. And I love to engage with the community. I've been working on this for 10 years or more. And currently, I work at NVIDIA at the cloud native team, where my job day to day is to see how can we make Kubernetes adopt all the new technologies that we as NVIDIA are exposing. So we do from driver publishing to a scheduler, right? So we can now do from ResourceSlices all the way to kubelet and CDI. So this is everything we are doing in Kubernetes to enable the entire subset of GPU features. And again, not just GPUs, but now the problem for me at the Kubernetes side of the house in NVIDIA is my problem is not just GPUs. I need to care about NVLinks. I need to care about interconnects. I need to care about memory. And since Grace, now I also need to care about CPUs. So starting with Grace and now coming with Beta, NVIDIA is also shipping CPUs, not just GPUs. So these CPUs also come with a lot of awesome features that if in Kubernetes, for example, you request just a CPU, you are basically wasting resources or underutilizing your CPUs. So this is why we are introducing all of these special technologies into Kubernetes. And I will be talking about them. So on the device plugin, it was the classical path, but now I will be showing you what is DRA. So on DRA, we have ResourceSlices, ResourceClaims, device classes. We can even request a GPU, but say, hey, I want a GPU, but my process really doesn't need that much memory. Give me a GPU and just give me 1 GB of memory from that GPU. Like we can be that specific when requesting resources to Kubernetes. So we can prepare a node, schedule, and request and arbitrage all from the dynamic resource allocation. That is the new way of injecting GPUs. So before, it was just like, give me 8 GPUs. You will get 8 GPUs from Kubernetes. Kubernetes would simply look for 8 GPUs in the system and allocate your 8 pods or 1 pod into a node with 8 GPUs. In the DRA era, you can set attributes and capacity. So it's not just give me 8 GPUs, but it's give me 8 GPUs with this specific memory, with MIC capability or MPS capability. Give me a node that has confidential containers capability. Like you can be very fine-grained when you are requesting a pod on Kubernetes today. So I really want to get to the YAML file. So I've seen a lot of faces on like how it's done. Just bear with me. I'm trying to introduce this topic. I know this is a very Slurm heavy crowd, so we are getting there. So, but when we look this from very far away, it looks the same, right? Like the device plugin path and the DRA path are the same. No matter what are you requesting, we do some processes internally in the controller, and then we use CDI, the container device interface, to tell the kubelet what to inject into the pod. So at the end of the day, you are getting the same. You are getting a pod that is getting a CDI injection, and with that CDI, the pod, container D or cryo knows what to do and which special devices to inject into your container. So at the end of the day, you get the same list, The difference is that you can be more picky about that list. This is how you can request a GB200. Let's say you have a GB200 cluster and nothing else, right? Like it's a homogeneous cluster. So you can simply say, give me 4 GPUs. Where? Do you need them NUMA where? Do you need them close to each other? Basically, Kubernetes is going to give you a node that has 4 GPUs or 2 nodes with 2 GPUs each. That's all Kubernetes can do in the previous way. Now, you can be very specific. You can define that you need a GB200 because perhaps you have a cluster that is heterogeneous. So you have H100s and A100s from like previous procurement processes in your company. So now your cluster has all GPUs and new GPUs. So you can be very specific. You can tell, give me GPUs that are GB200s, and this feature here, the click. So the click means give me GB200s that are connected with NVLink. So now, when you are preparing for an MPI process, you declare a GPU like this, and you will know that your GPUs are being shared by NVLink, and this will allow for NVLink interconnect. So this is what we are seeing as a community. This is the change. I know from a YAML point of view, or from a declarative point of view, looks a bit more complex, but HPC and, for example, AI is all about complexity, right? Like, we want to be picky about where do we launch our processes. What do we have now? Where are we going? Right now, we have DRA. It has been evolving. We can now declare ResourceSlices, ResourceClaims, device classes, but all of the rest is upcoming on future releases of Kubernetes. So that's why I'm trying to use colors here. But if you look for these numbers on the Kubernetes GitHub webpage, you will see that our topics that are being discussed as a community, it's really hard to get there. The last one, I'm putting it in a special color, is because the meetings about this topic have been very fun to have, and we need more people from the HPC community to join these meetings, because we are discussing how to inject CPU and memory as DRA citizens, right? As of today, memory and CPU are managed by the kubelet itself in Kubernetes. But we want the CPU and the memory to also be special devices. So basically, everything on the node will become a special device. So we are going to stop just assuming the CPU and the memory are there, but the new CPUs and new memories are dynamic. We can, on hardware, partition the CPU, partition the memory, and do a lot of fun things. I'm not a hardware person. I'm a software person. And this comes with a lot of caveats that we need to have in mind when scheduling pods into these special CPUs. We are discussing partitionable devices, dynamic MIG. As of today, for example, when running on device plugin, you need to pre-configure your GPUs and your Kubernetes cluster with the special MIG configuration that you need for your GPUs. Coming soon in Kubernetes, you will be able to do it dynamically. So you don't need to be stopping, reconfiguring MIG for your GPUs, and then starting again your Kubernetes cluster. You can just schedule a pod, and the pod will say, oh, by the way, I just need half of a GPU, or I need a quarter of a GPU, and everything will happen automatically, run by Kubernetes and run by NVIDIA software. We will do everything dynamically. Also, consumable capacity. You can request fractional and shareable devices. So as I was saying, we are preparing to say, hey, I want a GPU, but from that GPU, only give me 1 GB of memory. Like, leave the rest of the memory free for another process. Like, we can be that specific. But all of that is coming. So it's in beta. When something is named beta in Kubernetes, it means that it is on by default, but when you are starting your Kubernetes cluster, you can request it to be off, right? Once it goes GA, it's harder to turn it off. Multi-node NVLink made declarative. So this is something that is very special for us, is scheduling on top of an NVLink enabled GB200 cluster is really hard. So we created a special concept that is the compute domain. For those who understand Kubernetes, a compute domain is basically a Kubernetes API, a native API, so a common cluster resource definition, so CRD. And you can declare, as I will show, I have the YAML file coming forward, how many nodes do you want? And internally, we are going to go and create deploy pods and deploy daemon sets, enable IMEX. So when you deploy your nodes, your process will see all the nodes as a single node using the NVLink and IMEX capability, and then you can run your process there. And once your process is done, using the compute domain controller, we will clean up everything and be ready for the next job. So how does it, when you are scheduling, so you request the process, then it communicates that to the NVIDIA DRA driver. The NVIDIA DRA driver deploys a set of pods as a daemon set on the IMEX enable nodes. Then we declare them as connected. You can run your process, and we take care of turning it down. Why it must be dynamic? We need it to be security isolated, fault isolation. So as we all know, sometimes a node can fail. So we need to be able to plug and play a different node, and the controller is smart enough to do it. So if you requested a 4-node processes doing the compute domain, and one node goes down, the controller is going to be smart enough to get a new node and plug it into your IMEX rack, in your virtual IMEX rack, right? And it's for cost efficiency as well. Here. So here is how a compute domain looks like. So basically, you name it when you are declaring it, and then in the workload itself, so this is a deployment, and this is how you declare the compute domain. You declare that you need a special compute domain, right? The number of nodes, as you have there, it follows the workload. So the workload can request, as I have there, 18 replicas. So from the 72 GPUs that you have in your GB200 rack, you can request 18. So we internally, with the NVIDIA DRA, we make sure that when you run a process, your 18 GPUs are going to be NVLink connected. So you don't have to do anything. The compute domain API is going to take care of that. Beyond the whole GPUs, so this is what I've been telling. So we have now ways to do partitionable devices, consumable capacity, and CPU and memory as special resources, not just default resources. So a resource slice is, before device plugin, you cannot do that, but now with DRA, you can request, give me a GPU with just 20 gigabytes of memory, or when you declare your GPU, you can set a special valid values. And this is something the admin can do. So it is open to the admin to do it, depending on the type of GPUs that you buy, right? Like if you have a GB200, H200, Beta Rubin, whatever. So this is up to the system admin to configure which values do they want to have available for their users. And then the users can request GPUs with a specific capacity, because again, there are some processes that are GPU heavy but not memory heavy. So you want to leave the memory free for those processes that are memory heavy but not GPU heavy. So you can play with that. Before, as of today, sometimes when you deploy a process, the process blocks the memory, but it's not really using the memory. Now you can, because the capacity is consumable, and you can split it out depending on the architecture of the GPU that you have. And also partitionable devices. So when you are declaring, when you install a new GPU in your cluster, you can create kind of like vetted MIG profiles. So for those system admins in the room that understand what a MIG profile is, so you can create slices that then when the user is requesting the workload, they can request a profile, a MIG profile. So give me a GPU that is a 3G 20 gigabytes, right? So you can request a specific MIG profiles, and all of this is going to be dynamic. So on my right side is going to be what the system admin configures, and on this side is what the user requests, and it's totally dynamic. So now, HPC primitives are coming into Kubernetes. So as I've been hearing during many coffee breaks, people were still thinking that this was very, very far away for Kubernetes, but now you can see that Kubernetes is even getting ahead of what Slurm and any other resource scheduler give you, because now Kubernetes is giving you the whole system admin package, the cloud capabilities, the auto-scaling, but now we are also going for the fine-grained control of resources, treating everything as a special resource so you can be very specific when you are scheduling your workloads in Kubernetes. So now, preparing for the QE and doing a stop for the next talk, all of this opens the door for something really fun that we are doing at NVIDIA and as a community, that is Slurm and Kubernetes being friends and playing together. So now that we have DRA and that we no longer request GPUs just saying, give me one GPU, we have attribute-based and topology-aware claims, we can do HPC with Kubernetes. And all of this is upstream, right? Like, all of this is on the Kubernetes official repository. The NVIDIA DRA was donated to the CNCF, so it's not even on the NVIDIA GitHub webpage. It's on the Kubernetes webpage or on the GitHub webpage. And as you can see, there is Kubernetes-6/DRA driver GPU. So everything is in the open. We are working as a community on this, and we are looking forward for more contributions. And with this, we stop for a small round of questions before my second block.
Thank you, Eduardo. So, any question for this first block?
Did I spoke too fast?
So, thank you for your presentation. I have a question. So, I can imagine, because I have some background on DevOps, the benefits of Kubernetes, and you also mentioned some of them. But how you will combine, like, someone who has been always working with Slurm as a system administrator, that this is better and he wants to change to Kubernetes?
Yeah, so I love the question because it's wording that we want to prevent. Nothing is better than nothing, right? So Slurm is open source, it's a community. Kubernetes is open source, it's a community. And we are trying to have them play side by side instead of saying Kubernetes will kill Slurm. So the messaging is, we will always have Slurm. Is how do we integrate Slurm into Kubernetes, that Kubernetes is becoming basically the operating system for distributed systems, right? So with Kubernetes, we have all the automation in place that Slurm doesn't have. Because Slurm for years has been very focused on being a very good workload manager, and that's Slurm. Kubernetes is not good at that. So Kubernetes gives you self-healing, monitoring, Grafana and all of that, Prometheus. So like things that system admins love, but Kubernetes is not good for scheduling, for workload management. So if we get them to play together, then you have the Slurm capabilities with all the system management package that is Kubernetes, right? So that's what we are trying to do here.
Okay, thank you so much.
Other questions?
I have one. So in one of your slides, you mentioned CRO. I was wondering how this actually works.
And where?
And it was one of the early slides. So basically, it's a mechanism as well to perform checkpoint and restart, which it's extremely important, especially when we are talking about long-term simulations, right?
Yeah.
But moving to these massive scale systems where NVL72 is just one unit, how you are going to push all this data into, I don't know, local file system, shared file system? Is the system able to digest this like nothing, or
not like
so? What are the challenges?
Not like nothing, but with NVLink. So the idea is that if you're not using the entire 72 GPUs on the system, there is bandwidth on the NVLink to move data around. So we can use the NVLink to move data and do checkpointing. So that's still, again, as I'm showing, things that I'm showing here are roadmap, not available yet. So we are still trying to work that with Kubernetes, because CRI-O itself for Docker was still like it was GA like last year or something like that. So it's very fresh. Now we are trying to see how can we map that into Kubernetes. So it will take maybe another couple of years to get there, but we are already discussing it as a community. And we are trying to pull as many people we can into the topic, because it's really hard. Yeah, because checkpointing in Kubernetes is not just checkpointing the process, it's checkpointing the entire topology of where the process was running. As NVIDIA, what we are doing is that we open sourced the project that is called Topograph, that helps you get the entire topography of the system. And it's even, as I'm going to show in the next talk, it helps Slurm make decisions on top of Kubernetes. So that system will also help with checkpointing. And we also have node-aware and NUMA-aware topology. So we can get the topology of the node and the topology of the system and save that as metadata. So that is already available. What we are is like, how do we do the checkpoint of the entire system?
Any other question from the audience?
Do you need more water?
Huh?
Do you need more water?
Oh, no, it's okay. Is that I speak too fast because I have 2 talks, so I'm not even looking at the clock. So if I run through my 30 minutes, that's more than okay. I want to really, really leave room for questions because half of what I'm presenting is discussions in the community right now.
Water is coming.